and she attended level 1 this year of MTTS. And Mugdha's topic for today is a proof of fundamental theorem of algebra using linear algebra. Yeah, Mugdha, you can share your screen.
Thank you, sir. I will share my screen. Okay, I am going to discuss a proof of the fundamental theorem of algebra using linear algebra. First of all, some history. The first widely accepted proof of the fundamental theorem of algebra was published by Gauss in 1799. Though that proof had some gaps according to today's standards. And then many other proofs followed, including 2 more proofs by Gauss, by D'Alembert, by Cauchy, and many other people. And they can be divided roughly into 3 categories, namely topological proofs, analytical proofs, and algebraic proofs. Today's proof is an algebraic proof, and more specifically, it is a proof using linear algebra. And it was given by Ham-Dugson, which was published in 2003 in the American Mathematical Monthly. And I am going to discuss a modification of this proof, which I learned from the expository articles by Professor Kumaresan and by Professor Keith Conrad. Okay, let's first recall what is the fundamental theorem of algebra. It says that if you take any non-constant monic polynomial with complex coefficients, then it has a 0 in C. For example, our Px is a given polynomial x raised to n plus an minus 1 x raised to n minus 1 so on plus a1x plus a0. Then there exists a lambda in C such that P of lambda is 0, where all these coefficients are complex. And generally, we encounter this theorem in linear algebra course to prove the following theorem. That theorem says that theorem 2, suppose V is a non-trivial finite dimensional vector space over C, and if A is a linear map from V to V, then A has an eigenvalue. That means there exists a non-zero vector V in V and a lambda in C such that AV is equal to lambda times V. And how do we prove this using the fundamental theorem of algebra? If we consider the characteristic polynomial of this linear map A, it will be a non-constant polynomial of degree equal to dimension of vector space, which is greater than or equal to 1 with complex coefficients. So by fundamental theorem of algebra, it will have a 0 in C, and that 0 is nothing but an eigenvalue of this linear map A. Okay, that is the way how we prove theorem 2 using theorem 1. And the interesting thing is that even we can prove the theorem 1 using this theorem 2. That is, the fundamental theorem of algebra can be proved using theorem 2. For that, we will have to produce a linear map whose characteristic polynomial will be the given linear map. Sorry, it will be given monic polynomial. So we have to prove the fundamental theorem of algebra. So we have given a monic polynomial x raised to n plus an minus 1 x raised to n minus 1 plus so on plus a1x plus a0, which is a polynomial over complex numbers. Then we can consider the companion matrix of that polynomial. How that companion matrix looks like? It is an n cross n matrix whose last column consists of all the coefficients which are negatives of the coefficients in the given monic polynomial, minus a0, minus a1, minus a2, so on up to minus an minus 1. First n minus 1 entries of first row are all zeros, and remaining n minus 1 cross n minus 1 matrix is the identity matrix of order n minus 1. And one can check that if we consider the matrix X times identity matrix of order n minus a, then its determinant is the given polynomial. That means the characteristic polynomial of this matrix A is the given monic polynomial. We are assuming theorem 2. So by that we know that A has a eigenvalue in C, and that eigenvalue is nothing but a 0 of the given monic polynomial. So this is how we prove theorem 1 using theorem 2. So it is sufficient if we prove the theorem 2 in order to prove the theorem 1, but theorem 2 should be proved independent of fundamental theorem of algebra. And that is what we are going to do in this seminar. For that, we will need some lemmas. First lemma is that any polynomial of odd degree with real coefficients has a real 0. Many of you would have seen in the real analysis course. We prove it using intermediate value theorem. And using this lemma, we can prove the following lemma. Suppose we have odd dimensional real vector space, and if we take any commuting linear maps A and B on V, that means AB is same as BA, then they have a common eigenvector. That means there exists a non-zero vector V in V such that AV is equal to some lambda 1 times V and B is equal to some lambda 2 times V, where lambda 1 and lambda 2 are real numbers. And lambda 1 and lambda 2 may be different. We are just claiming that they have a common eigenvector, may not be common eigenvalue. Okay, and one more lemma we will need. What is the assumption? We are fixing a field F and an integer d greater than 1 with what property? That if you take any vector space V over that field F whose dimension is not divisible by d, then any linear map from V to V has an eigenvector. This is our assumption. Have you seen such a situation where this hypothesis holds true? For example, if you take field to be of real numbers and integer d to be 2, then what will be the situation? You will have an odd dimensional real vector space. So its characteristic polynomial will be of odd degree, and by lemma 3, that polynomial will have a real 0, and that will be an eigenvalue of our linear map on real vector space of odd dimension. So it will have an eigenvector. So you have something similar to lemma 4. And what is the conclusion in lemma 4? That in such a case, if you take two commuting linear maps from V to V, then they have a common eigenvector. So we want to generalize this lemma 4 in this situation in lemma 5. That if we have a field and integer d greater than 1, such that every vector space over V over a field F whose dimension is not divisible by d, then such a vector space on any linear map on such a vector space has an eigenvector. Then we want to conclude that for such a vector space V, every pair of commuting linear maps on V has a common eigenvector. So this is a generalization of lemma 4 with F equal to R and D equal to 2. The hypothesis seems to be very restrictive, but let's see how to use it to prove our theorem. And one more lemma we will need, that every complex number has a square root in C. This is very distinguishing feature of C from R. In R, every number need not have a square root in R. We will use this property of C in our proof. Okay, now we are ready to prove theorem 2. Let's start. We will do it by some type of induction. Let me tell you first what is our theme behind proving this theorem 2. That means we have a given complex vector space, non-trivial complex vector space, and any linear map on that vector space. We have to prove that that linear map has an eigenvalue or equivalently an eigenvector. We will treat our linear map as a matrix, n cross n matrix, where n is dimension of V. And we will try to construct another non-zero matrix B such that AB is equal to some lambda times B, where lambda is a scalar complex number. Then what will happen, as B is non-zero, B will have a non-zero column vector, say Bj. then A times Bj will give us jth column of AB, but AB is nothing but lambda B. So jth column of AB will be lambda times Bj. So we got A times Bj is equal to lambda times Bj, where Bj is non-zero vector.
Yeah, Mugdha, your slides are not visible to me.
Yeah, I'm just talking.
Okay, all right.
So if we construct such a B, then we will get an eigenvector of A. That is what we are going to do in the full proof. So suppose dimension of V is n. Our proof will be by induction on the highest power of 2 dividing n. So we will write n as 2 raised to k times n dash, where k is greater than or equal to 0 and n dash is odd. That means we are pulling out all the powers of 2 from n and writing n as 2 raised to k times n dash. And our induction will be on this k. Can you tell me what will be the base case where we would like to start our induction? Okay, we will start with k is equal to 0, right? Can you describe what will be the case k is equal to 0? If k is 0, then n will be odd. So we want to prove that if we have an odd dimensional complex vector space, then any linear map from V to V has an eigenvector. Let's see how to do that. For that, we will treat our linear map from V to V as matrix. We will fix some basis of V and consider matrix of A with respect to that basis. And we will associate to that matrix A some linear map on some vector space of matrices. What is that vector space? It is a real vector space Hn consisting of all n cross n matrices M such that M star, that means conjugate transpose of M, is same as M. That is, it is the set of all Hermitian matrices of order n. And we are considering it as a real vector space. Can anyone tell me what will be the dimension of Hn over R? See, as it is a Hermitian matrix, all the entries on the diagonal will be real. So diagonal will contribute n, and all the above diagonal entries will contribute 2 each towards the dimension. There are n into n minus 1 by 2 entries above diagonal. So the dimension of Hn over R will be 2 times n into n minus 1 by 2 plus n, which is n square. As n, we are assuming n is odd, so n square also will be odd. So we have a odd dimensional real vector space Hn. And we have seen in the lemma 4 that in such a situation, if we have a pair of commuting linear maps on that vector space, then they have a common eigenvector. We will use this. So we will try to construct 2 linear maps which are commuting on this vector space Hn. We know that if we take any n cross n matrix, complex matrix, then we can write M as m plus m star by 2 plus I times m minus m star by 2i, where m plus m star by 2 and m minus m star by 2i, these both matrices are Hermitian. We want to do something with A times B, this product. So we can write AB as AB plus B star A star by 2 plus I times AB minus B star A star by 2i, where both these real and imaginary components are Hermitian. In particular, if I take B from the set of Hermitian matrices Hn, then what will happen? B star will be equal to B. So the above equation will become AB is equal to AB plus BA star by 2 plus I times AB minus BA star by 2i. And from this equation, we get a motivation to define linear maps on Hn, T1 and T2, given by T1b is equal to AB plus BA star by 2 and T2b is equal to AB minus BA star by 2i, where A is matrix of linear map A from V to V, which we have fixed. And for every Hermitian matrix B, we are assigning to A these two linear maps, T1b and T2b. And note that AB can be written as T1 times B plus I times T2b. Okay, and one can check that T1 and T2 are indeed linear maps from Hn to Hn and they commute with each other. So by lemma 4, what do we have? That T1 and T2 have a common eigenvector. Let's call it B. So B is a non-zero Hermitian matrix such that T1b is equal to lambda 1 times B and T2b is equal to lambda 2 times B, where lambda 1 and lambda 2 are real numbers because Hn is real vector space. And AB can be written as T1b plus I times T2b, but T1b is lambda 1 times B, T2b is lambda 2 times B. So we get AB is equal to lambda 1 plus I lambda 2 times B, where lambda 1 plus I lambda 2 is a complex number. So this is the situation which I was looking for. So if I consider now B is non-zero, so I can consider a non-zero column vector of B, then it will serve as an eigenvector of A with eigenvalue lambda 1 plus I lambda 2. Okay, so if V is a odd dimensional complex vector space and A is a linear map from V to V, we have constructed an eigenvector of A. So we are done with the base case. Now let's see what is our induction hypothesis. So what will be induction hypothesis? If our V has dimension n such that the highest power of 2 that divides n is less than 2 to the power k. In other words, 2 to the power k does not divide n. Then every linear map on such a complex vector space has an eigenvector. This is what our inductive hypothesis will be, and we will assume this for k greater than or equal to 1. Now this reminds us of some hypothesis which we have seen. Can you point it out? If you see lemma 5, then we were saying this for some fixed f and integer d greater than 1 with what property? Every vector space V over f whose dimension is not divisible by d, every linear map from V to V has an eigenvector. If you replace f by c, field of complex numbers, and d if you take as 2 to the power k, then what our situation is? If you take any complex vector space whose dimension is not divisible by 2 to the power k, then any linear map on such a vector space has an eigenvector. So if we replace in lemma 5 f by c and d by 2 to the power k, then we exactly get our inductive hypothesis. So we can use the conclusion of lemma 5. So assuming inductive hypothesis, by lemma 5 we will get any pair of commuting linear maps on a complex vector space of such a dimension, that is 2 to the power k does not divide dimension of V, then that pair of commuting linear maps has a common eigenvector. Remember this, we will use this to prove our main step. So now what we will assume, we are going to the main step. Let dimension of V be n and the highest power of 2 that divides n be 2 to the power k. And T from V to V be a linear map. We want to prove that T has an eigenvalue or equivalently an eigenvector. For that, we will fix an ordered basis of V and let A be the matrix of T with respect to that basis. So we have to prove that A has an eigenvector. We want to use inductive hypothesis. So we will try to construct some complex vector space whose dimension is not divisible by 2 to the power k, and assign linear maps on that vector space to this matrix A. Let's see how to do that. We will consider the space of all complex symmetric matrices of order n. Let's call that space as sim Cn. All n cross n matrices complex whose transpose is same as the original matrix, M transpose equal to M, that is symmetric matrix. And one can see that This is a complex vector space of dimension n into n plus 1 by 2. Now note that our n is such that the highest power of 2 that divides n is 2 to the power k. We are dividing by 2. So n by 2 has the highest power of 2 as 2 to the power k minus 1. And since k is greater than or equal to 1, n is even. So n plus 1 is odd. So 2 to the power k does not divide n into n plus 1 by 2. Okay, so we have a complex vector space whose dimension is not divisible by 2 to the power k. Okay, so we can apply induction hypothesis, and we have seen a consequence of inductive hypothesis by using lemma 5, that if you take any pair of commuting linear maps on such a vector space, then it has a common eigenvector. So Dirksen considered the following linear maps from sim Cn to sim Cn, L1 and L2, given by L1b is equal to AB plus BA transpose and L2b is equal to ABA transpose. And these are linear maps from sim Cn to sim Cn, and they commute with each other. So by lemma 5, we can say that they will have a common eigenvector. L1 and L2 will have a common eigenvector, say B, which is a non-zero complex symmetric matrix of order n. Right? So now we have L1b is equal to AB plus BA transpose is equal to lambda B, and L2b is equal to ABA transpose is equal to mu B for some lambda and mu in C. Now we can use the value of BA transpose from this equation in the second equation. We will get BA transpose is equal to lambda B minus AB, that we will substitute here. We will get mu B is equal to A times lambda B minus AB, and which we can rewrite as A square minus lambda A plus mu times B is zero matrix. And if we consider the quadratic equation corresponding to this matrix equation, we will get Z square minus lambda Z plus mu is equal to 0. This is the quadratic equation in C. So we can use the quadratic formula, standard quadratic formula, to find the roots of this quadratic equation. And that formula involves square root of a complex number. But by lemma 6, we know that the square root of any complex number is again a complex number. So we will get complex square roots. We will get complex roots to this quadratic equation, Z square minus lambda Z plus mu is equal to 0. In other words, we can factorize the polynomial Z square minus lambda Z plus mu as Z minus alpha times Z minus beta for some alpha and beta in C. Note that this is where we are using the complex vector space. We cannot do this with real vector space. A real quadratic equation need not be factorized as this using real linear factors. And then again we can come to the matrix equation using this quadratic equation. We can write it as A minus alpha times A minus beta is zero matrix. So A minus alpha times A minus beta times B will be zero matrix. Now there are two cases. A minus beta times B can be 0, or A minus beta times B can be non-zero. Suppose A minus beta times B, this matrix is 0. Then what will happen? We will get AB is equal to B beta, which we were looking for. Now if you take any non-zero column vector of B, then it will be an eigenvector of A with eigenvalue beta. And what will happen if A minus beta I times B, this matrix, is non-zero? Then we will call it some matrix C. Okay, A minus beta I times B is C, suppose. Then we will get A minus alpha I times C is zero matrix. In other words, A times C will be equal to alpha times C, and C is a non-zero matrix. So any non-zero column vector of C, that is A minus beta I times B, will be an eigenvector of A with eigenvalue alpha. So in any case, we will get an eigenvector to A. Okay, so we have proved that if we have a non-trivial complex finite dimensional vector space, and if we take any linear map from V to V, then it has an eigenvector or equivalently an eigenvalue. This was what we wanted to prove. And we have already seen that fundamental theorem of algebra can be derived using this theorem. So we have proved the fundamental theorem of algebra using linear algebra techniques. Okay. So this completes the proof. Thank you. If anyone has any questions or any comments, then you are welcome.
Yeah, any questions? Mugdha, did you already mention about some reference for this?
Yeah, while speaking, I had told that this proof was given by Dirksen. The main proof can be seen in the American Mathematical Monthly of 2003. And this is the modification of that proof. And I learned that from the expository articles by Professor Kumresan and Keith Conrad.
Yeah. So, in case there is no question, let us thank Mugdha for the nice, wonderful talk. Yeah, with this, we finish today's session.